Hi. Today we'll be providing an outline of our project, which has shifted a bit since we presented last December. Our current project is relieVR, which is a bioresponsive virtual reality program for treating lower urinary tract dysfunction, also known as LUTD. So lower urinary tract dysfunction affects about 20% of children with incontinence and improper voiding, causing daily disruptions and psychological distress. Left untreated, LUTD can lead to renal scarring and urinary tract infections, and is usually a cause of insufficient coordination between the brain, bladder, and muscles surrounding them, but it is treatable through training. Current at-home training methods, however, fail to address the lack of coordination and simply provide methods for preventing unintended voiding. Biofeedback, a technique where real-time physiological signals are transformed into meaningful visual cues to help patients learn to control certain body processes, is also used to treat LUTD, among a variety of other conditions. These sessions, however, use expensive equipment with cumbersome, outdated, and unengaging software, and patients also fail to visit the clinic often enough for sessions to be as effective as they should be. Virtual reality has started being used in hospitals, and because of its ability to make immersive, dynamic experiences, it makes a good fit for biofeedback therapy. So with all this in mind, our goal then was to create a bioresponsive virtual reality platform for administering biofeedback therapy for at-home treatment of LUTs that could be self-operated. So at a high-level view, our project consists of three major components: the EMG circuitry, transmission between the microcontroller to the headset, and the virtual environment within the headset. So EMG signals are taken from the perianal and abdominal muscles and processed through circuitry that is attached to a belt for the patient's comfort. The circuitry processes the signal and transmits the data through Wi-Fi to the headset, which then modifies the visual output.
This is the circuit we built to take in raw EMG signals and convert them into detectable and analyzable signals for the Arduino. I'll walk you through each step of the circuit. First, the EMG electrodes record raw signals from the patient's perianal and abdominal muscles. They are then passed through an INA-126 instrumentation amplifier, which turns the 3-channel EMG into one signal, filters out any potential 60 Hz noise, and adds a gain of 5 to the signal. Through frequency analysis of the raw data, we found that the majority of relevant EMG data is in the 10 to 150 Hz range, with everything else being noise. In this stage, the output signal is passed through a high-pass filter with a cutoff of 10.3 Hz to remove DC offset, followed by a low-pass filter with cutoff 159 Hz to remove high-frequency noise. Finally, the Arduino can read a range of 0 to 5 volts, and the EMG data at this point is on the scale of millivolts. We thus pass it through an op-amp with a gain of 1000 to make the signals distinguishable before inputting the signal into Arduino for further processing and analyzing.
During our last presentation, we mentioned that we would be switching from Bluetooth to Wi-Fi for the communication protocol between the microprocessor and the Oculus. We first experimented with the Arduino Maker Wi-Fi because this microprocessor has a built-in Wi-Fi module, but it only supported UDP broadcast, which is a less secure method of data transmission, so our data kept getting lost. Ultimately, we decided to use an ESP standalone Wi-Fi module that can easily interface with the Arduino and the Arduino IDE. This Wi-Fi module supports TCP data transfer, which is a more secure method since it first establishes the connection, then sends data across. The ESP module is connected to an Arduino Uno, sharing TX and RX lines. The Arduino receives the input from the EMG sensors, sends the data to the ESP module, which can then send it to the Oculus. This is an example of a successful communication between the ESP module and my computer. All I had to do was connect my laptop to the ESP module's access point Wi-Fi that I set up. Then I could telnet using the IP address of the access point to send and receive data.
To engage the pediatric users, we are building a VR version of the Scoops game with 2 modes of EMG control. The environment is built using Unity and can be packaged into an application to be used with the Oculus Go standalone VR headset or with a smartphone on the Samsung Gear VR. Here is a demo video of our game without EMG input. The user is placed within a calming forest environment and has a control array to interact with objects, as shown by the changing reticule of the pointer, such as the cone or an object for EMG calibration. Upon selecting the cone, the game begins with ice cream scoops falling from the sky. The perianal EMG signal would control the horizontal movement of the cone, but in this instance, it is moving towards the direction of the pointer. Once 3 scoops are stacked, the player begins to advance upwards into the air. If a scoop is missed, it falls to the ground. In the future, we will also add a second mode of control for the abdominal EMG and information regarding the player's progress, such as the number of scoops stacked.
Our device's battery life is long enough to last at least 1 session, if not more. The EMG sensitivity is based on current biofeedback systems used to treat LUTs. Our cost breakdown mostly included the cost of the headset and EMG.
We met with a few times with Dr. Van Batavia, a pediatric urologist at CHOP, who was very excited about our project and eager to help us test it on patients. He agreed to help us recruit patients and allow us to test in his clinic, estimating 3 trials a week based on his patient schedule. Validation of the efficacy of our device would be performed through a bladder scan to determine bladder fullness after voiding, and the uroflow to observe voiding patterns after use of relieVR. We wrote several surveys for important stakeholders for before and after relieVR use to collect qualitative data and determine how to improve our device. For the patients, we would ask about their thoughts on the current biofeedback system and their experience with technology. Then afterwards, we would ask them how they liked our Scoops game and what they found uncomfortable about the system. We would ask caregivers about the satisfaction with the patient's frequency of treatment and progress. Importantly, after using the system, we would ask the caregivers whether they would feel comfortable running a session at home to ensure that our system is feasible as an at-home device. Lastly, we would ask the clinician about the patient's compliance and their thoughts about relieVR's setup. We had initially planned to perform clinical testing during the end of March and early April, with a revised and finished product by mid-April based on testing and survey responses. However, due to the impacts from COVID-19, we were unable to demonstrate our prototype to the urology department at CHOP and will not be able to perform clinical testing and validation for our device. For now, we are planning on demoing our game to determine how we can make it more engaging and are brainstorming other ways to test and validate our device.
VR biofeedback therapy has a large potential to impact treatment of LUTD for pediatric patients. In addition to LUTD, VR biofeedback is being used to treat a number of indications such as chronic and acute pain, PTSD, and mental health. We spoke with Joe Powers, Penn grad and CSO of Applied VR, which is the first company to penetrate this market. Their headsets are undergoing clinical trials in 250 hospitals with over 30,000 patients. They hope to serve as the clinically approved hardware platform upon which software for other indications, such as LUTD, may be added. We have been selected as finalists for the Johns Hopkins Healthcare Design Competition and will be pitching our project virtually in mid-April with the potential to win prizes and get feedback from expert judges. We'd like to thank Dr. Batavia and nurse Monica Moran for being welcoming mentors and teaching us about LUTD and its biofeedback therapy at CHOP. We'd also like to thank the Stevenson Foundation Laboratory and Makerspace and other mentors and organizations which have lent us equipment and guidance for this project.